In this lesson, we're going to continue working on the idea that we saw in the last lesson with polynomials in factored form. Last lesson, we kind of saw how to sketch them from their picture. Here, we're going to kind of go back and forth between the two, or sorry, how to sketch them from their function, equation, I should say. But we saw the importance of the form of the factored form, like what it looks like, and the x-intercepts and how they related to each other. And we're going to see if we can abuse that a little bit more to make our lives easy when it's coming up with modeling different polynomial functions. So right off the bat here, we've got a picture of a quadratic, and we could find an equation for this using either vector form or factored form that we saw back. Standard form is a little tricky to come up with right from that graph, but we could do it a couple ways anyway. But because we're going to want to work with general polynomials, we're going to do it in factored form. Before we get there, I'm going to point out that the name of the lesson is the roots and zeros of polynomial functions. These are other words that mean something pretty much the same thing as x-intercepts. I don't want to get too much into the details of how they differ from each other definitionally. I'm going to say that for our purposes, we can use the three terms interchangeably. We can talk about the x-intercepts of a function. We can talk about the zeros of a function, which are where y is 0, which by definition is x-intercept, or the roots of a function, which is just another word for the same thing. The differences between the words, to give you an analogy, is we often talk about quadratic functions, and parabolas as being the same thing. Technically, the mathematical expression that you write down, f of x equals, is the function, and the picture that you draw is parabolic or a parabola in shape. But we often use them almost interchangeably because we know they really mean the same thing. Here it's the same idea. Technically, a function doesn't really directly have x-intercepts. A graph of the function has x-intercepts. And likewise, it's a very similar use of the words, but we're going to just, like I said, use them interchangeably, pretend they mean the same thing. So looking at the picture we've got, which is a quadratic function or a parabola, the x-intercepts are pretty obvious. We've got one over here at -1 and one over there at +3. So those are our x-intercepts, and we can use those to find the equation of the function in factored form. I'm going to leave a little space there and point out that the first bracket is going to be x plus 1, the opposite sign of the -1 we had as the x-intercept, and the second bracket is x minus 3. The reason the sign is opposite is because we want each of those brackets to be 0 when we plug in the x-intercept. So when I plug in -1 for x in the first bracket, I get -1 plus 1 is 0. And in the second bracket, I plug in a 3 and get 3 minus 3 equals 0. Now, we did mention that there should be this a value in front, this leading coefficient. I can tell from the graph that it's positive because we start high and end high, but I don't have an exact value. I made this one easy by observation to say that from our vertex, we go over 1, up 1, over 2, up 4. And because of that, this is actually just going to be a 1 in front, so we don't even really need it there. If it was a different value, we'd have to find it. And again, we'll get to that in our next lesson, which is the last lesson, exactly how to find that more precisely. Okay, so as I was saying before, the x-intercepts are what gives these zeros, what gives us 0 when we plug them in. So we know our function looks like f at x, and when I plug in x equals -1, so f at -1 is -1 plus 1 times, oops, it's no longer x, it's -1, minus 3. We get 0 times -4, which is 0. And when we plug in 3, we get 3 plus 1 times 3 minus 3 is 4 times 0, which is 0. So this is why they're called zeros. 0 is what we get when we plug in the x-intercepts. And again, roots is just another name for both of those terms as well. So question 1, determine the roots of the function f at x equals 5 times x plus 4 times x plus 2 times x minus 3. And for our purposes, another way of wording that question would be find the x-intercepts or find the values of x that give y equals 0. Find the zeros. So I think we can really quickly by observation say that the values of x would be -4, -2, and +3. So basically what we did in the last lesson, we're looking for the things that we would plot as the x-intercepts. The only difference here is I'm calling them roots, but you're still finding the same numbers. Determine the zeros of g at x. Well, that would be x equals -2, 0, 3, and 4. Simple enough. Okay, I'm just going to stop with the general idea and do like semi-real world problem. This is something that I've done with different classes, and it's a cool little activity you can do where you get a piece of paper, a piece of cardboard, and you try to make the biggest volume bin out of it that you possibly can. So all you have to do is cut squares out of each of the four corners, and we're just going to say those squares are x by x, and we want to see what x value is going to give us the biggest volume for the box. So what we know is that the volume of a box is going to be length times width times height. Or depending on which variables you want to do, x times y times z or whatever. But either way, it's kind of a this times of this times of this kind of thing, whatever you want to call those values. So for us, the volume of our box is going to be dependent on x, how much we cut out of each corner. So we'll call it v at x. Now that's going to be a length times a width times a height. We'll do this one first. The distance from here to here, we know is 20. We do know it's 20. But we want the distance from here to here, which is going to be the width of our box. And once we've taken 20 and we've cut an x off of each sides, we're going to be left with 20 minus 2x. And then we want kind of this value here between those pieces. And that would be a total height of 12. So I want to be careful about my use of height here. It's height in the two-dimensional picture, but it's actually going to be the length of the three-dimensional box. Either way, that's going to be 12 minus x on the top minus x on the bottom. 12 minus 2x's. And then finally, the last dimension will be the real height of the box, which will just be x. Now, technically, I can just leave it there, but I'm going to do one other little thing. I'm going to notice that in my first bracket, 20 and -2 are both divisible by 2, as are those. So if I factor a 2 out of the first bracket and a 2 out of the second bracket, that's going to leave me with 4, 2 times 2, 10 minus x, 6 minus x times x. Now that looks like a cubic with 3 separate parts, 3 things in the bracket, each with instead of an x minus, it's a 10 minus, or a number minus x, but really it's the same thing. Okay, so from that, what values of x would give a volume of 0? So really what we're doing is looking at the zeros, or the roots of that equation, and we can see that we're going to get zeros when x is 10, 6, or 0. All right, now we want to sketch a little bit of a graph of that. You'll notice I didn't even put a y scale on here because we haven't been really focusing on what the y values are. So we might as well just leave it off. We're looking for a general shape. And we know that there's an x-intercept at 0, 6, and 10. Now here's the other thing we know. This is a little bit hard to see because it's not x minus, it's something minus x, but we have a minus in front of that x and a minus in front of that x and a positive. A minus times a minus times a positive is a positive. That means that the leading coefficient will be positive. And we're going to have an x cubed. And a leading coefficient that is positive with x cubed means we're going to start low, end high. So our graph, somehow my picture, there we go. Picture moved a little bit. Means we're going to basically start down here, go up here a little bit, down, and up again. So our graph's going to look something like that. There's our cubic positive leading coefficient, and it's trying to tell us what the volume is at different values of x. Now I'm going to point out that when we talked about domain and range before, we talked about all possible inputs and all possible outputs. Domain is everything you can put in, range is everything you can get out. And we were talking about mathematically without breaking the function. Now, if we just take a quick moment and look back at this picture, I think what you're going to see is that x can be as small as 0. X obviously can't be negative. I can't possibly have, let's blow this up a little bit. I can't possibly have a negative value for x. Something like I can't cut out a negative square from each corner. And likewise, if x is any bigger than 6, that means that once I've cut 6 out of this corner and 6 out of that corner, I have zero left for the width of the box, because 6 and 6 together is 12. So there's nothing left once I've cut 6 out of the top and 6 out of the bottom. So I know that x realistically can't be any smaller than 0 or any bigger than 6. And if I go back to my general picture there we are. I think what we're going to see is the only part of this that's valid is from here to here. Anything where x is less than 0 doesn't exist. Anything where x is above 6, even though it goes positive again, mathematically, it really doesn't make any sense. Because in order to be positive, we'd have to cut more than 10 out of each corner. The thing's only 12 by 20. Cutting more than 10 out of each corner is going to leave us with no paper at all, so it won't work. So I think the realistic domain for this is going to be x is the element of real, such that x is between 0 and 6. Now, I should actually back up a second. X could be 0, but that would give me a volume of 0. And x could be 6, but that also gives me a volume of 0. Basically, I'm just taking a piece of paper and folding it in half. I think I should make these so that they're strictly between 0 and 6. Not less than or equal to, but actually just less than. And I could also write that if I wanted to, as the domain is 0, 6. And I'll just remind you that the round bracket says that the 0 and the 6 are not included. Everything just above 0 and anything up to really close to 6 is, but the 0 and the 6 themselves are not. Okay, so that's the kind of thing that we get in a real application. The question doesn't ask us for it, but just for the heck of it, let's flip over to Desmos and see what this graph actually looks like. And I think we can see that the volume at x is, what did we say it was? 4, 10 minus x, 6 minus x, and x. Looks like this. And again, it's very stretchy, so I'm going to fix it in a moment. I know all the good stuff happens between x equals 0 and 10, but I got to go down a little bit and go to maybe -4 and 14, just so nothing gets cut off. So qualitatively, we had this right. 0 is kind of our start. 6 is as far as we can go. Anything above this doesn't really work. By the way, we can actually do this in Desmos. So if I go up here beside my thing, you won't have to do this, but just out of interest's sake, if beside my equation I use the squiggly bracket notation and say that 0 is less than x is less than 6, it'll actually cut off the part that is irrelevant and only show me the part that actually is used in this question. Okay. Again, we don't have to worry about that. We can just focus on the part that matters, but that is the actual realistic domain for this question. Cool. Okay, so something we might want to know is what is the exact value of x that gives us the maximum volume, or sorry, the volume of x that gives us the maximum volume of the box, and what is that volume? And so we just look at where this gets its largest point, and it turns out that we can get a volume of 262.68 cubic centimeters if we use an x value of 20.42 centimeters. Okay, so not bad. We can solve a real life problem algebraically or using Desmos as a little bit of an equation thing. All right, coming back. The last thing I want to get to today before we get to tomorrow's lesson or the next lesson on actually doing our final full modeling of polynomial functions is to just talk about roots of order n. So far, this question here had 3 x-intercepts. It's a degree 3, so it has 3 different roots. Sometimes we don't get different roots. We get roots of higher order. So here's what I want you to notice in this graph here. I've progressively taken basically the same parabola and just kept shifting it upwards a little bit more and more. So here, when the parabola looks like this, we have x-intercepts of 1 and 5. The vertex is at 3. So the vertex is right down the middle is 3. And we have x-intercepts that are 3 minus 2 and 3 plus 2. Fair enough. If I shift that up a little bit, our 2 x-intercepts become 2 and 4. They've gotten a little bit closer to the 3, a little bit closer to the middle point. And if I go to the next one, my x-intercepts are 2.5 and 3.5. They're now only half away from the middle point. And if I edge it up just a little bit more, what ends up happening is there's now only one root, and that happens to be 3. But it was really 2 separate roots that just kept getting closer and closer together. So you could think that right before it hit this point, there must have been 2 roots, one where it was 2.9999999, and the other one was 3.000001. But they're essentially 2 roots of 3. And what we say in this case is that we still have 2 roots. There's just one value with an order of 2. So we say there's 2 roots there. How do we recognize these in a picture? It's actually easier than you think. I look at where the x-axis intercept is right here. I'm going to just blow up that one. And I notice that my parabola doesn't go through the x-axis. It just touches it and then goes back to where it was coming from. So there's just this one brief moment, erase, where the graph goes completely flat. It just touches the x-axis and goes back to where it's coming from. And that tells me that there's an order 2 root there. Because if it went just a little further, it would go through the axis twice. It would go down below it and then up back through it. So that's an order 2 root, something that just touches the axis. Similarly, here I've got a cubic with 3 roots. The first one is 2, 0, and negative 2, 0, and 2. The middle of that is the 0, and then the other 2 are plus and minus 2. This one is 0 plus or minus 1. And then as we keep getting a little bit closer, we get 0 plus and minus a half. But they're very close. And here we only have one number, and that's 0. Well, if you think about this, this is just x cubed. So the only value of x that will make that 0 is 0. But we can think of that as 3 roots. They're just all the same. They're all zeros. So zoom in on that one. How do we tell when we have an order 3 root? The answer is that it goes through the axis just like an order 1 root would, a regular root. But as it's going through the axis, it just briefly, very briefly goes flat. If it goes flat like that, it's an order 3 root. If it touches the axis and bounces back, it's an order 2 root. And if it just goes through diagonally, it's an order 1 root. Now, I will say that to be really technical, we could have something that does this that's an order 5 or an order 7 or an order 9 root. They're almost impossible to distinguish, so we're not going to deal with them. If it touches the axis just once, it's order 2. If it goes flat as it goes through it, it's order 3. And if it just touches, if it just goes through diagonally, it's order 1, it's a normal root. So let's see if we can actually apply that. So for our first one here, we have f at x equals 3 times x minus 2 times x plus 1 squared. We're going to pay almost no attention to the fact that the leading coefficient there is a 3. we do care that it's positive, but the actual value of 3 is irrelevant. It just stretches or squeezes a little bit, and we're leaving the y values off here, so it doesn't matter. What I will note, though, is my x-intercepts are 2 and -1. However, the -1, you'll notice that that bracket has a square on it, which means that at -1, it's going to go flat, but it's not going to pass through the axis. All right, so we have an order 1 root, the regular root. We have an order 2 root. That's a total of degree 3. We get basically one root of 2 and 2 roots of -1. So that means it's going to be a cubic with a positive leading coefficient. It's going to start down there, end up there. But instead of going through the axis on the first one, it's coming up, touching and going back down. Oops, let me actually do that in blue. Touching, coming back down, then going up through. So it looks just like other cubics. It's just been shifted down a little bit so that there is no part that goes above the axis on that first touch. It just touches, comes back down again. Similarly with the second one, we have an order 1 root at x equals -3. An order 2 root at x equals +2. That means it's going to go flat and then go back to where it came from because of that order 2 there. So when we draw this, just before we draw that, we have a cubic. It's got a negative leading coefficient, which means it starts high, ends low. So it starts high, goes through the axis at the regular root, comes up, just touches the axis and goes back down again. So the order 2 root, it does not pass through, just glances off of. This one's similar. We've got an order 3 root and an order 1 root. The regular root is a -2. The other one is a +3, and it's got to go flat at that point. But because it's an order 3 root, it's going to go flat, but it's still going to pass through the axis. Now, in this case, we have an order 1 and an order 3. That's a total of degree 4. This is going to be a quartic, which means normally it would start high and end high, except it's got a negative leading coefficient, so it starts low and ends low. So it has to go through the first one, and then as it comes down, it has to go through the second one, but it has to go flat first. So it looks like that. And if you're curious how any of these exactly look, by all means, just open Desmos and throw the functions in, and you'll see exactly how they look. But we're just looking for the general kind of qualitative shape. All right. The next one, we put in x equals -3 is 1 root, and that's going to go flat. That's an order 2 root. And then at 1, we're going to go flat as well. That's an order 3 root, though, so it is going to go through the axis. As a whole, this is an order 5, a degree 5, order 2 plus order 3, degree 5. So it's going to look kind of like a cubic. It's going to start down here, end up there. It has a positive leading coefficient. So we have to follow the rule of the first one has to touch, but come back. And then the second one has to go flat and then through. So it's going to look a little something like that. I'll agree it's probably a little bit wonky, but again, for general shape, I think that's good enough. All right, the last couple here. This one, I just used pi as the coefficient. It really doesn't matter. It's, like I said, it's just some real number. What matters is the roots and their orders. So here I have a root of 1 and its order 2, so it'll go flat and back through. Here I have negative, I think I said 1 and drew -1. Flat at 1, flat at -2. Both cases, it's going to touch and go back where it came from because of the order 2-ness. And because the leading coefficient is negative, this is going to start low, end low. So degree 4 would normally start high and end high, negative in front takes care of that. So this is going to end up looking kind of like the letter M. So something like that. And finally, a big leading coefficient of 42, but again, the actual value is irrelevant. It's positive. We have an order 2, an order 3, and an order 2 again. That's a total of degree 7. All odd polynomials that with a positive leading coefficient start low and high. So we already know it's going to start low and high. We're going to have a double root or an order 2 root at -4. So it'll go flat and go back. At -1, it will go through. And at 3, it will go flat again. So flat, flat but through, flat. And it should look something like that. Oops, hit the wrong button. Okay, and just to finish off, I'm going to run over to Desmos and we're going to see what that one actually looks like. So that's f at x equals 42x plus 4 squared. So there's our part that looks kind of like a parabola. And then x plus 1 cubed. And that's the part there that looks kind of like a cubic. And then finally we have an x minus 3 squared. So we get something else over at 3 that looks kind of like a parabola again. A very, very, very sharp parabola until I zoom in a lot. But you'll notice that if I do zoom in enough, it does actually go flat. Okay, that was kind of crazy actually. So I'll go back here and that's what the graph looks like, which does not look like our picture. Our picture looked like this. But that's because this is a little bit wonky. So what I'm going to do is go into here and I'm going to just really, really shrink the Y, or I should say explode it so that you can see a lot of it. And I have no idea what the maximum or minimum will be here. So I'm just going to go from -1,000 to +1,000. We'll adjust as necessary. All right, and you can see it still goes way off. How much further before we actually get everything in? Try this again, go from x equals -2 to 7. Sooner or later, we're going to see the qualitative stuff. Okay. So that's more or less what it looks like. Up, glances off, down, flat, up, down, glances off, goes back up. Compare that to our drawing. Down, glances off, up, through, up, down, glances off. Yep, that's actually pretty close. Again, the heights of our graphs are a little wee bit different, but that's okay. The heights of the bumps and how far they go up and down is a little bit different, but the qualitative parts are still there. The shape is still there. So I think we did a pretty good job, given that I think this took us longer to do in Desmos than it did to draw it by hand. Okay, I'm going to stop there then. If you scroll down, you'll see that there are some practice problems here. Give these a shot. I'm asking you the degree, the end behavior, and the x-intercepts of each of these. Then you're going to do a rough sketch. And I have not given you the actual full functions in the final answers, but you can throw these, like pictures of the functions in the final answers, but you can throw them into Desmos to see if they're qualitatively like your sketch. Give them a shot, see how it goes. If you've got problems, make sure you let me know. And I will see you in the final lesson of the unit coming up next.